Hello and welcome to MiniLecture 26 on Riemann sums. So this is the first of our last set of lectures in this class on integrals. And a Riemann sum is going to be a way of approximating an integral and where we can take the limit of a Riemann sum and get an integral. Alright, so let's first do some review about functions and discrete functions. So we talked about discrete functions in this class before, where we have some function a of n is equal to some function of n, for example, n minus 1 squared plus 2. Here, little n can be any index that is an integer, so we could have a1, a2, a3, a4. So for example, in the case of this sequence, we have a1 equals 2 and so forth. All right, suppose that we want to add all of the values of this sequence together. Is there a better way of doing this? Okay, so if we wanted to do it longhand, we would have to write a1 plus a2 plus dot 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 up to a10. And that's really annoying, but there is luckily something called sigma notation, which lets us do this really efficiently. So sigma notation, we write this large Greek letter sigma, and then we introduce an index. In this case, our index is I. So here I equals 1 up to I equals 10 of some quantity ai is equal to a1 plus a2 plus all the things up to plus a10. So we count from 1 to 10, and this sigma is a way of saying to sum all those things. So for example, we have this sum here. Now notice that our index starts at 3, so we start by plugging 3 in for I. So we have 3 halves plus 4 halves plus 5 halves plus a whole bunch of other things until we get up to 12 halves. All right, so that's a fast way of writing this sum here. We can do it for something more arbitrary. So for example, suppose we have f sub minus 1, then we can write this in sigma notation by doing sigma from I equals to minus 1 up until we want to count all the way until 13 of f of I. Now notice that there isn't just one unique way to write a sigma. There's also, we could do it with a different index where I starts at 0, for example, and here we're doing this one is 0, this is 1, this is 2, this is 3, and so forth. And so we have f of I minus 1, and we want to sum all the way up until 13. Well, if I plug in 13, I'd have 13 minus 1, which would be 12. So I want to sum all the way up to I equals 14, not I equals 13, so that we have 14 minus 1 is equal to 13. So these are two ways of writing this sum right here. All right, so that's sigma notation. All right, so now, some more review about something that you guys should be very familiar with from your secondary school math, and that is the area of objects. So an area of a right triangle, if this distance is A and this distance here is B, then the area of this triangle is A times B divided by 2, and that is because it is half the area of a square or a rectangle where we have a side A and a side B, and if we multiply these two together, we get the area of our rectangle. Similarly, we can use the same knowledge to calculate the area of more complicated objects. For example, this pentagon right here, if we draw this line here and call this line B and this A here, so that a whole side here is equal to 2A, then the area of this rectangle is A times B over 2, and this rectangle is A times B over 2, such that the area of one of these triangles is A times B divided by 2 times B, or just A times B. So we have A times B, A times B, and A times B. So that the whole area of this is 5 times A times B. All right, so that's the area of some well-known geometric objects, but what if we want to find the area of some weird object, such as the area underneath this weird curve here? So let's call this weird curve here f of x. Since we are into functions in this class, how do we figure out the area underneath some function f of x between some point A and some point B? How do we do that? All right, so let's do that here. So we have some point A, some beginning point, some ending point, and some function f of x. How do we find the area underneath it? Well, the first way we can do it is we can divide that area up into rectangles, and we can sum all those rectangles together because we know how to find the area of a rectangle. So if we sum a whole bunch of rectangles together, we'll get an approximate area for the area under this curve, and that sum is called a Riemann sum. So this is a special type of sum called a Riemann sum. All right, so how do we find this area? Well, let's think about what each one of these little rectangles is. First of all, we have this distance here, which is delta x, and we have this distance here. We need our height and our width. Well, that distance here, this curve point, is the function evaluated at -5. So if we plug in -5, that will be the height of our rectangle. We can plug in f of -4, and that would be the height of this rectangle. And then we want to multiply each of those heights by the width, delta x. What is delta x in this case? Well, we go from -5 to -4, so delta x equals 1. So we have delta x equals 1, and we can sum delta x times the height of our rectangle from I equals 1, 1, 2, 3, 4, 5, 6, 7, 9, 10. We do that for 10 different rectangles here, and we get the approximate area under the curve. So the orange area is given by that, and that is the Riemann sum of 10 intervals that approximates the area under the curve. So here we could do it with 20 rectangles. Here, what is our delta x? Well, we start at 0, for example. So we have x equals 0, x equals a half, x equals 1, x equals 1.5, x equals 2. So the distance here is delta x equals 0.5, gives us 20 rectangles. We figure out the height of our rectangles in a very similar way. So, for example, here we have f of 2, and here we have f of 3.5, and we're going to multiply f of x, from I equals 1 to 20 of delta x. Okay, and similarly, we could do the same thing with 40 rectangles where delta x equals 0.25. And notice that the area that you're missing, all these little blue triangles in here, get smaller and smaller and smaller. I mean, here we're almost missing nothing at all. So as those rectangles get narrower, as you get more and more rectangles, the better your approximation is. All right, so that is the conceptual or graphical view of a Riemann sum, but how do we do the formal definition of a Riemann sum with n rectangles? All right, well, we have to consider where we're going from and to. So if this quantity down here is A and this quantity up here is B, then delta x is the total distance we travel, so the distance between A and B, so B minus A, the final minus initial, divided by how many rectangles we want. So we have B minus A divided by n. All right, now we have to multiply that by f of xi. How do we do xi? Well, we have to say, where do I start? So xi is the point that you start at, A, plus how many ever delta x's you add. So if you add 1 delta x, you have I times b minus a over n. If you want to go 2 delta x's, then you're going to multiply by 2 delta x's. So this quantity here is delta x, and you're going to multiply by how many ever delta x's you have. All right. So you have a plus I times delta x. All right, and that gives us our width and our height, and you multiply all those together and you sum them, and that gives you the area of your rectangle down here, of all your rectangles down here, which approximates the area of your curve. All right, so that is the idea of a Riemann sum, and once again, the more ends that we have, the larger the number of rectangles, the better the approximation is. All right. So this gives us the idea of a Riemann integral. So we're going from a Riemann sum to Riemann integral is the case where we take the limit as the number of rectangles gets absolutely enormous, so it goes to infinity. So once again, we have our delta x and we have our height. Now, if we're dividing by something that is really big, then our delta x is going to get really small. So this delta x is going to get smaller and smaller and smaller. And so we simply write this as a little dx because we go from having a small run to an infinitely small run. So this is the same idea as the derivative, except now we're using it as the width of a rectangle. Now, our function f of x now just goes to a continuous function f of x, and instead of writing this sum here, we stretch that sum out so that it has a curly shape, which is called the integral sign, and we're integrating from the point A to the point B. So if we take the limit of the Riemann sum as the number of rectangles gets enormous, the delta x ends up going to an infinitely small little delta x, and we end up with our integral of our function between the initial point and the final point with respect to x. All right, this gives us the idea of some properties of integrals, and the first one is that this integral of f of x dx between the point A and the point B represents the area under the curve. Remember that the Riemann sum is an approximation to the area under the curve, but if we let that approximation get infinitely good, then the integral is the exact area under the curve between A and B. Second of all, if this curve f of x goes below 0, what does that mean? So if we have some area here, what do we do about this area here? Are we counting this area under the curve, or are we counting this area above the curve? So specifically, if the integral represents the area of x above the x-axis minus the area below. So what we're saying is we have this area above minus this red area plus this green area. And once again, this also comes from the Riemann sum, that if we draw a whole bunch of rectangles, we'll have some positive area rectangles here and some negative area rectangles down here. So in this case, I've evaluated the x for you in all of these different green points, and the y value, the point here, the point here, the point here, the point here, the point there, and the negative values from here, 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 and here. And what do we get? Well, we first have to calculate our delta x. Our change in x here, delta x, is equal to 1. And then we want to take all of the positive values. So we have some of the values that are above 0. So this one is above 0. And then we have all of our values below 0. Below 0. And we want to multiply all of these values by delta x and sum them. All right, so if I take the sum of all of these things here, I end up getting 180. So the sum of all those green things is 180. Similarly, the sum of all these green things is 180. The sum of all of these red things is minus 125. The sum of all these red things is minus 125. So I end up with 180 minus 125 minus 125 plus 180, which is simply equal to 110. So that is the area above the curve. We don't have to worry about the delta x here because that delta x is simply 1. And we have the area below the curve plus the area above the curve. All right, with that, I'm going to leave you with this question about measles, where you're going to calculate the area under this incidence curve or this infectiousness curve over time.